لي كده شايف الاي بي فيرجن 4 عامل ازاي؟ يعني it's crowded كده تحس ان crowded. So go back to for just an IP. ايه؟ طيب بسم الله الرحمن الرحيم. So we finished discussing IP version 4 and as we said one of the limitations for IP version 4 was the exhaustion of the IP space. And we talked about some technologies that have been introduced with IP version 4 to try to keep IP version 4 surviving as long as possible. اللي هم ايه؟ اتكلمنا على ايه؟ NAT is one with CIDR. In network one actually we talked about also one of the technologies اللي هي variable length subnet mask or VLS. That was all, we did not discuss it here in class. But these are all technologies or amendments to IP version 4 to try to keep IP version 4 surviving as long as possible. Another, although a school of thought, they thought about a revolutionary change in IP to try to resolve the issue of the IP exhaustion once and for all. So they talked about IP version 6. So the initial motivation for IP version 6 was to introduce a larger IP space which solves this problem once and for all. However, of course, there are some challenges in IP version 6. One of them is the gradual deployment, and that's what we need to discuss today. Another additional motivation that we also sort of hinted about last time was to try to use the lessons learned from the design of IP version 4 to try to make the header for IP version 6 cleaner and really keep the fields that make sense and they are actually being used for a critical functionality. Other fields such as اتكلمنا على fragmentation and reassembly صح؟ This has been removed completely from IP version 6. We don't do any fragmentation and reassembly. Okay, so we'll talk about if we remove the fragmentation, what is the implication and can we do it in other ways or we don't have to do it? And if we don't do it, what if we encounter one of the hubs that uses مثلا wireless, which means that the maximum transmission unit has been reduced, so what do we do? So also there is the motivation for providing quality of service. IP version 4 used to provide quality of service? Yes, in a way, yes. We talked about DSCP, اللي هو differentiated services code point. We talked about the field called differentiated services, right? So there is a traffic class in IP version 4. Although IP version 4 standards did not really define how this field is going to be used. It's up to the deployment or the service provider to really use this field in any way. But we don't use it مثلا for routing, definitely. And we just keep it in the field, but how it's going to be used is not part of the scope of IP. So IP version 6 tried to build on this and introduced another level of quality service that we will need to talk about. So one of the things that we tried to keep in IP version 6 was the fixed length header. We talked about the variable length header for IP version 4, and that was because of what? Because of the existence of one of the fields was actually making the header length dynamic. Lower which field?
It's called
options. The options fields. The options field has a variable length in the header. It's part of the IP header. And the length for this options fields is variable. But this options field was almost never used as part of IP version 4. It was not used for anything. So that really complicated the header structure for IP version 4 for no reason. So in IP version 6, they removed the options field. So many things have been removed in IP version 6. So the options fields have been removed. Options. The fragmentation and of course reassembly. We talked about checksum as well. Checksum field was removed. I told you we need to provide some kind of error checking, right? So checksum was used for error checking. So if the packet was corrupted on the way for some reason, then we have to check for this and ignore the packet or discard the packet. So how come we remove the checksum? The idea is that experimentally they found that the probability for any corruption of the packet in the core network was extremely low. Extremely low, because the core network is mostly wired. Remember, it's not like wireless. The core network is usually wired. It's not like wireless. Wireless, احنا عارفين fading, multipath fading, probability of error is high. But in the core network, we don't typically use wireless technology in the core network. So the possibility of packet corruption in the core network is 10 to the power مثلا minus 20 ولا حاجة, which is يعني next to zero. So the error checking in the core network has no meaning. And it's an overhead that's not really utilized well. So all these fields have been, طبعا options fee, yes, all these fields have been removed. طبعا when we talk about fragmentation, we talk about the identification, fragment offset, and the flag. All of these have been removed. Okay? But there are some other fields that have been added back. And there are some other fields that have been renamed. That's what we need to talk about. IPv6, it's so this is the header structure for IPv6. As you can see, it's a lot cleaner if you compare this to capture this in your mind here, and much more in terms of مثلا length for the address and things like that. It's much more, but it looks cleaner. So of course, something like the version is fine. DSCP, اللي هو differentiated service code point, they call it priority. It's simple. Why DSCP? Priority خلاص يعني, it's simple. But they introduced another field بقى. Okay, this field is 20 bits. 20 bits. It's called flow label. This flow label, this actually labels a flow from the name. What is a flow? What is the definition of a flow? A flow is defined as stream of packets that is going from one source to one destination with the same characteristics. With the same characteristics. بمعنى, if I have a host, and this host has some processes running. These processes, they produce some packets or some data, right? There could be هنا a process that we talk about a web browser. This web browser has content. This content has video, audio, graphics, text, things like that. Each of these is actually a separate flow. So even if we are sending all this data from the same source to another destination, okay, each of these series of segments that belong to the same source and the same destination with the same characteristics. So even if you change the video, if you change to audio, if you change to graphics, this is different flow. So in other words, a composition of one web page is actually more than one flow being composed into the web page. Video, audio, graphics, text, things like that, okay? So each of these flow is for us like series of data units which have the same sort of characteristics, okay? Type. What IPv6 tried to do is that to say, so I can provide per flow quality of service. So IP introduced the per flow quality of service. Okay? So, which means that based on this set of data units that belong to the same stream of packets that goes from one source to one destination, we can provide spatial behavior for this flow. Okay? That's new. IP version 4 did not do. IP version 4 provides a per class behavior, not per class, يعني priority. IP version 6 still maintains the priority. But within a traffic class that has the same priority, we have hundreds of these flows, right? So we can even zoom in and provide flow behavior, pair flow behavior. Okay? طيب, I was expecting someone to مثلا say that, okay, isn't this virtual circuit? Huh? ما هو احنا in virtual circuit, remember when we talked about virtual circuit, we said that we can provide virtual circuit number that sort of identifies a specific logical circuit.
Yeah, it is
صح؟
kind of logical.
Huh?
It is kind of logical distribution.
Logical distribution for logical distribution for different flows, right? That goes to the core network, right?
Yes.
This is different from virtual circuit, definitely. But why? يعني are we regressing back to virtual circuit routing? Yeah. This is per flow A, quality of service. It's not used for routing.
But it's very important in IoT.
Very important in IoT.
Yeah. Because you need
احنا we're talking about the core network. Remember احنا هنا يعني احنا inside the core network now. IoT ده this is a sensor deployed somewhere in the street is giving us some data. But هنا we're talking about the core network. Do we really need to know that we need to provide specific يعني behavior for the data that is coming from this sensor? Maybe yes, maybe no. But what I'm trying to say is that what is the difference between pair flow quality of service and virtual circuit? Virtual circuit uses virtual circuit number for what? For routing. No, for routing. For routing, virtual circuit number is maintained in the routing table. معايا ولا لا؟ Virtual circuit number is used for routing. So we provide routing based on the virtual circuit. Per flow here is only for quality of service. Quality of service is different from routing. Quality of service, we provide some distinction for a specific flow, okay? Some specific distinction like what? We give high priority. So we give high priority for this flow that it has to go first. Whenever we have a flow that has a specific flow label, we need to have high security. We need to pass this flow as fast as possible. But routing has nothing to do with that. We don't use it for routing. واضح? This is not a state. Remember, in virtual circuit, we talked about maintaining a state for each virtual circuit in the routing table.
Here
If you remember.
I'm creating a label. I'm not saying what I'm doing.
لا, you're not. لا, a label is set in the packet. What we're trying to answer now is that what do we use this label for? What do you use this flow label for? We use this label for providing quality of service per flow. Okay? So it's not only a traffic class, because a traffic class معناها ايه? All the traffic on the internet can be divided into 4 classes. Okay? Regardless of where it's coming from, regardless of where it's going to. So we divide the entire traffic of the internet into 4 classes. So this is a very coarse way of classifying the traffic, صح؟ The flow label بقى gets inside one of these classes and say, لا, I can even كمان inside this traffic class select a particular flow, okay, and give it a specific behavior. A specific behavior in terms of quality of service, but we never use it for routing. We never have to store this flow label in the routing table. We never do this. If we do this, then we go back to virtual circuit. This is virtual circuit. We have to store the entire state of the flow, depending on where it's coming from, where it's going to, okay? And we store the state of that virtual circuit inside the routing table. But here, no, we don't do this. عرفنا الفرق؟ We may provide pair flow behavior, but never, ever use it for routing. This has nothing to do with the routing table. واضح؟ ماشي كده؟
الدكتور لما تكون top of the class
Hmm?
ما
Hmm?
بعد استخدم المي كلاس
لا هو البرايورتي اهو.
على
priority yes, priority yes.
تمام.
طيب payload length هنا one thing that has been that also vanished as you might يعني of course no one really followed the previous material so you do there was a field in IP version 4 called the header length. We used to have header length because the header was variable صح? We don't have to do this here because the header is fixed. It's 40 bytes. Okay? In IP version 4, it's minimum 20 bytes to 60 bytes. Why? Because we have the options fields was actually 40 bytes and it was never used. Here we decided to clean these things up. So we don't have any header length. We have the payload length, best. Payload, of course, because the data part is variable. Of course, the data part is variable. We know that. So we need to have payload length. That's for sure. But the header length was removed. Next header corresponds to, in IP version 4, corresponds to the protocol field. Remember, we talked about the protocol field. It always points to the protocol in the upper layer. Here, we don't call it a protocol, we call it next header. But it's actually, it has similar functionality. But they called it next header because it's not necessarily pointing to the protocol in the upper layer. It could be in the same layer, actually. We'll talk about one of the scenarios where next header is actually used to point to a next header in the same layer even. So for IP version 4, this used to be points to TCP or points to UDP or points to ICMP. Okay? But here, it could actually point to IP version 4. We'll talk about this. Okay? This corresponds to a ايوه هاب ليميت اللي كان اسمه ايه؟ ايوه TTL. برافو عليك. فهير it's meaningful. We called it time to live and it was never time. It was never used as time. It used to be called hop limit. So here we put the meaningful name يعني. Other than this, we have the source address, the destination address, and that's it. But هنا طبعا the source address here is 128, which means actually we have هنا four rows خد بالك. Each row is 32 bits.
What will tell me if a packet is corrupted?
We answered this question. We removed even the checksum was removed.
Okay, so
Which means is that why? Because here again, هنا we're talking about the core network. So the possibility of having packet corruption in the core network is none. Is almost none. Because in the core network we're talking about wired network mainly. It's not wireless. So the possibility of error is really very, very, very low. Okay? واضح كده؟ So the header is cleaner, neat, and type. What about fragmentation and reassembly? We don't have any fields related to fragmentation and reassembly, صح? طيب what happens for IP version 6 when it comes to, because IP version 6 will potentially be used for different hubs. So what if I'm going from Ethernet to wireless to kaza to kaza to kaza? Okay? So that's an issue. So IP version 6, it kind of uses fragmentation and reassembly, but in a different way. What happens is that the router, before it sends, the router, I'm talking about the default gateway. The default gateway, when it sends to the core network, when it sends the packet to the core network, it tries to estimate the maximum transmission unit across the entire end-to-end section, or entire end-to-end path, all the way to the end. Okay? I can estimate this, yes, in a way. So I can say, okay, so let me use 500 bytes, which means that for wireless, it's 500 bytes, and for Ethernet, it's more. So if I use 500 bytes, I will be safe that I will not actually use any kind of fragmentation, صح? Because I'm using 500 bytes, which is the maximum transmission unit for wireless. Okay? So most probably, if I use 500 bytes, I will not need any fragmentation in the assembly. So what happens if I go مثلا from wireless مثلا from Wi-Fi to Bluetooth بقى مثلا, and Bluetooth happens to have less maximum transmission unit. IP version 6 provides a troubleshooting message called packet too big. This is part of ICMP64. أو ICMP version 6 يعني. Okay? So for IP version 6, for ICMP version 6, if the router tries to send a packet on the next hop and it finds that the packet length is supposed to be smaller, I cannot do any fragmentation. Okay? But what I could do is that I will send back to the source saying that packet too big, please reduce it. فالsource هيعمل ايه؟ Source, I'm talking about the default gateway. Source اللي هو default gateway. The first router that tries to send these packets to the core network. So the default gateway will then try to reduce the packet. And if that default gateway uses IP version 4, it will be able to fragment. Okay? So we use fragmentation reassembly, but in a different way. But we don't maintain the fragmentation fields inside the packet header. One of the issues بقى, so طبعا checksum has been removed, as we said. Removed entirely to reduce processing time. Because we do error checking in the core network, and the possibility of really having data corruption in the core network is almost none. ما فيش. But we do lots of processing in the core net, تخيل millions and millions, billions of packets. We have to do error checking for the possibility of having one every. And remember, what if there is packet corruption? What happens if there is packet corruption? Okay, if you use TCP in the transport layer, well, TCP performs packet error checking, صح? And if it finds error checking, it will retransmit. So there's no issue. So we're actually doing lots of processing overhead in the core network for nothing. Again, the concept of pushing the complexity to the edge. Yes. Options fields allowed outside of the header indicated by the next header field. We'll talk about this scenario. So we may decide to somehow translate the IP version 6 header and put it inside the options fields of IP version 4. هنشوف ازاي. So ICMP version 6 now is a new version with some added. We talked about ICMP, we talked about ping and trace routes, we talked about these troubleshooting messages. Here we had to add other messages like packet too big, because I don't do any fragmentation and reassembly. So if it happens that I try to send a packet and the packet is too big, then I can send troubleshooting message to the source. طيب, the transition بقى from IP version 4 to IP version 6, this is one of the grand challenges that faced the designers of IP version 6. Because IP version 4, the whole internet is IP version 4 by default. So if we try to deploy IP version 6, we cannot really shut down the entire internet for a few days and update all the routers. So because the internet follows a decentralized architecture. Okay? So we cannot say, okay, so shut down the internet, all the service providers have to shut down, and we try to do the deployment synchronously. We can never do this. So it has to happen gradually. Okay? But gradually means that we will have IP version 6 parts of the network and IP version 4 parts of the network, right? But IP version 6 cannot talk to IP version 4 directly, صح? So this gradual deployment necessitated the need for some new technique that kind of bridges the gap between IP version 4 and IP version 6. Okay? So how will بقى the network operate with this mixed IP version 4 and IP version 6? Because we have to live with that for at least decades until we'll be able to phase out IP version 4. And it doesn't seem like it will be phased out in the next 10 to 20 years. Since I taught this 18 years ago, we've been saying that IP version 6 will be gradually deployed, and it has never replaced IP version 4 completely in the last 18 years. And I think for the next 1 or 2 decades, it will never replace IP version 4 completely. Okay? طيب. So one of the very important techniques that's used to kind of bridge and facilitate the inter-existence between IP version 4 and IP version 6 is called tunneling. So we talked about these concepts in Network 1, if you remember. So we talked about tunneling and we talked about IP translation as well. We talked about 2 techniques. IP translation is kind of rarely used. So the tunneling is the concept that's used. Before that, we need to talk about dual stack. So dual stack means that in the same node, in the same router, or the same حتى device, because we need to have a network layer, صح? In any device. So in any device, we need, first of all, a dual stack. Dual stack means that we need to have IPv4 stack, which includes what? Includes طبعا IP version 4, ICMP, DHCP. Remember, DHCP is an application layer protocol that's used for assigning the IP addresses to the different hosts. Okay? طبعا rep is a dynamic routing protocol. We'll talk about it as part of this chapter. OSPF, NAT. All of these are protocols that work hand in hand with IP version 4. And we have another stack in the same device. We have IP version 6 stack, okay, which will have ICMP version 6, DHCP version 6, and everything, and NAT 64. Okay, so these protocols work hand in hand with IP version 6 to deal with the IP version 6 format. Okay, so this dual stack will be in the same node, and that's easy because here these are software processes. So, for example, Windows 10 or Windows 11, they have dual stack IP. So it has the stack for IP version 6 and it has the stack for IP version 4. Both are there. So what does this enable us to do? This will enable us to have this device as part of a network that's IP version 4, or in the same geographical area. If we have IP version 6, we can use IP version 4 or IP version 6. So the same Windows machine or the same router, okay, that has the dual stack will now be part of IP version 4 network or IP version 6 network. Okay? But that's not enough. For us, that's okay, but that's not enough. Why? Because we also need to communicate between the 2 networks, which means that we need some kind of a switch or a bridging between IP version 4 and IP version 6. Okay? Which means that we need somehow to jump from here to here. So we need to do that jump. So the dual stack is good, but it's not enough. Okay? So that's tunneling. So tunneling allows us to bridge between IP version 4 and IP version 6. And by tunneling, I mean I will build a logical tunnel, okay, inside an IP version 4, or sorry, an IP version 6 communication. I will build a small tunnel of IP version 4. Or the other way around. I can build an IP version 6 tunnel inside an IP version 4 communication end-to-end. So that example shows this scenario. So typically, if I have imagine كده, if I have the tier 1 service provider, مثلا, if the tier 1 service provider has decided to upgrade to version 6, what is the implication of this? Everybody has to follow, صح? Everybody has to be version 4, version 6, صح? Because this IP service provider deals with many tier 2 and tier 3 service providers. Okay? So logically كده, tier 1 service providers usually are the last people to upgrade to IP version 6 or to the new technology. Okay? Because it needs to stay compatible with the old one, with the old technology. So the typical scenario is that the core network should still be IP version 4, and IP version 6 is deployed in the edges or closer to the edges. صح? Why? Because the closer it to the edge, the smaller the geographical area will be. I can really deploy this in a small area without affecting the entire internet. But if I deploy it in the core, this means that all the edges will be affected all at once. صح? There will be serious implications on all the edges all at once. I don't want to do that now. Okay? So the tier 1 service providers, usually they stay with IP version 4. So the more likely scenario is that we have tier 1 service providers or the core network, IP version 4, and I can deploy IP version 6 in smaller areas gradually. واضح كده؟ So if I have IP version 6 edges, then I have this border router. This border router بقى طبعا needs to have, first of all, needs to have dual stack for sure. This border router now has the dual stack. Okay? So that's first of all. But also it needs to have tunneling. It needs to have tunneling, which means I need to be able to switch from one stack to another. How do we do this بقى? It's very easy. احنا مش احنا عندنا هنا النتورك layer. This is the network layer, right? We receive the packet from, let's say, TCP. When we receive the packet from TCP, what do we do for the network layer? We append to it IPv6 header, صح? Okay? Then we send it down. Tunneling bar says, no, before you send it down, okay, do another encapsulation. Okay? Encapsulate IP version 4 header, okay, and make this the same payload. So from now on, all the underneath layers and the entire core network will see IP version 4, will not see IP version 6. Okay? So here, I will have to have IP version 4 header from now on. So that happens through another extra encapsulation inside the network layer before I send it down. So using the layer isolation, we talked about layer isolation as part of the protocol stack. Are we affecting Ethernet مثلا ولا wireless in any way? For Ethernet, for anything underneath, this is transparent, صح? We're not going to affect them in any way, صح? So we just need to do this extra encapsulation. That's it. Okay? And control, the most important thing is to control the source address and the destination address for this IP version 4. This is the most important thing. The source address will be the beginning of the tunnel, and the destination address will be the end of the tunnel. Why? Because at this destination, we need to do a detunneling, or we need to do the reverse operation. We need to do extra decapsulation step. Okay? So this way, خلاص, it's seamless. For us, it's a very clean approach. It provides the communication with a very, very minimal overhead. Just one encapsulation and one decapsulation, and we'll be able to do it. Okay? So that's explained here. So that's the scenario. So this border router will have to do extra. So here the source is A and the destination is F. So I need to send a packet from A to F. This is the original source and the original destination. When I incorporate the IP version 4 header, the source becomes A, B, and the destination becomes E. So this is the end of the tunnel. واضحة النقطة دي؟ So I need to modify the source and the destination. The source will be the beginning of the tunnel, and the destination will be the end of the tunnel. Why? Because this destination will have to do decapsulation. Extra step of decapsulation. If I do this, everything else is seamless. خلاص. Nobody will be affected. So tunneling is a very, very clean approach, very easy. By the way, the same concept is used for IPsec, IP security. It uses tunneling a lot. It's used in different protocols and different domains. Tunneling is a very, very clean approach, very seamless, doesn't cause any much overhead. Okay? Another technique that we talked about in Network 1, which we don't talk about it here, it's called the IP translation. IP translation, and I will not do tunneling. I will map the IP version 6 header to IP version 4 header. I will map it, translate it. So I will take the IP address, I will take the IP address, اللي هو ال IP version 6 address مثلا. I will truncate part of it and take مثلا the last 32 bits and use this as an IP version 4. Okay? So priority will be DSCP. Version will become 4 بدل 6 and so on. It will take each field. What about flow label? Oh, flow label ما don't have any correspondence. خلاص ارزعوا في الاوبشنز. حطوا في الاوبشنز كده. حطوا في الاوبشنز. اي حاجه anything that you don't know any corresponding mapping to it حطوا في الاوبشنز. Okay. That's what we have the options for. Okay? So IP translation is not a direct and seamless approach, and that's why it's rarely used. Rarely used. لأن there is a risk in the translation. You lose some information. But tunneling, we don't lose information, صح? We have to do this extra encapsulation and extra decapsulation, and everything else is seamless. We still maintain all the information.
Why would I ever need to know the IP translation?
They are used. It's a concept that's used. That's why I say it's rarely used. The protocol developers, they designed it, okay, but it actually introduces many restrictions. For example, how can you truncate 128 bits and make it 32 bits? This truncation may actually cause some IP duplicates, and it can produce issues. But they have designed it in a way that this is possible. Okay?
So you have to configure router B and router E.
Yes. To have dual stack, yes. Yeah. This is they need to have dual stack. Yeah. طيب تمام كده؟ طيب so this is IP version 4 and IP version 6. So these are topics that we covered so far. So we need to talk now about by routing algorithms. Of course, in network 2, not network 1. In network 2, we discussed dynamic routing protocols and static routing protocols. So we'll provide برضو quick review on this. And then we will dig deep into routing algorithms. These have not been discussed in any course before. Routing algorithms, we'll talk about بقى ايه the algorithm itself and what is the complexity and how it's actually implemented and so on. But first we need to talk about the difference between link state routing and distant vector routing. And of course hierarchical. Hierarchical routing is nothing but we're talking about two levels, two tiers. Each tier can either use distant vector or link state vector, or link state routing. So in one tier I could use distant vector, in one tier I could use link state. So you can consider it a hybrid approach between link state and distant vector. Okay? So we need to know the fundamental difference between link state and distant vector and what is the pros and cons for each one. ماشي؟ So of course, we talked about the difference between routing and packet forwarding. We talked about that before. We said that routing maintains a global picture or a global view to know that if I have a packet with this destination address, I know exactly the entire path where it has to go to until the very end. This is routing. So I need to plan the entire path. Okay? But فعليا يعني, in reality, what I do, each router, what it does is that it needs to forward this packet to a specific output port. That's what we call packet forwarding. Okay? So the router, when it receives a packet, okay, there is a planning that needs to happen that says that this packet should go through this until it reaches to the final destination. Okay? But what does this router do exactly at this point? It performs packet forwarding. It says, in order for this packet to go to this ultimate destination, okay, I need to send it to this output port and not this output port. That's it. This is packet forwarding. This packet forwarding is done in hardware. Remember we talked about router architecture and we talked about the switch fabric. This packet forwarding is the fastest process that needs to happen. That's why until now, even with software-defined networking, we still maintain this packet forwarding to be done in hardware because this is the fastest process that needs to be done extremely fast. Okay? But this planning is actually the brain, which can happen in the cloud. It can happen as a software process inside the router that kind of plans the entire path end to end. Okay? So imagine that the router is like, I need to go from QU to Dukhan. Okay? So I exit the gate and I have the intersection. This intersection could be like a roundabout. So there is a person standing in this roundabout. That's the router. Okay? So I ask this person, I need to go to Dukhan. Where should I go? He says, go left, go right. So this is packet forwarding. Okay? So this is packet forwarding. So when I go left or go right, hopefully I will reach to Dukhan. How? He may not actually give me any information. He says that all I know is just go left, go right. That's it. Okay? But how this will lead you to Dukhan, I don't know. واضحة النقطة؟ In Google Maps, مثلا, for example, we have the entire picture. We have the whole picture. ماشي? So we plan the route end to end. So it gives you the entire path end to end. Okay? But remember here we're talking about the network and we are inside one router in this network. So the question is, will this router have a global picture or not? Will this router have a Google map inside it? And what level? Should it have the entire Google map of the entire Earth? Is this gonna be scalable? This is kind of, violates the decentralization architecture of the internet. So we cannot really afford having one router maintaining a global picture for the entire internet. That's very, very hard. And if we do this is not a decentralized architecture anymore. Okay? So how do we compromise and address this trade-off? having sort of a global picture without having the global picture. Okay? So we know that routing talks about planning. Packet forwarding talks about one hop transmission of the packet to a particular output port. So inside the routing table, the router knows nothing but if you have this destination address, send it to this particular output port. If you have this destination address, send it to this particular output port. This is a packet forwarding. واضح كده؟ So one of the very useful techniques that we try to do is to do this route planning. Okay, is to do some graph abstraction. Graph abstraction طبعا is used in different disciplines. We use it a lot in many ways, صح? We use it in different disciplines. We use it حتى peer-to-peer network مثلا, for example, if we talk about peer-to-peer network. We talk about nodes that communicate files to each other مثلا. But underneath the topology of the actual network وكده we don't care about. All we care about is that there is TCP sessions between nodes وخلاص. We can use graph abstraction برضو to kind of abstract or model group of peer-to-peer nodes that communicate TCP segments to each other. We know we can do this. We use this as a system model a lot in any networking approach. Okay, so we can say that we can use graph abstraction, that we can represent each router as a node. So we have vertex, okay, and we have vertices يعني, and we have edges. So the vertices دي represent the router, and the edges represent the technology that's used from one router to another. Okay? So this way I can model the entire network into a graph. Okay? And then we can plan the routing algorithm and design the routing algorithm based on this graph abstraction. I don't have to worry about what's the technology here, what is the technology here. Okay? All I need to worry about is that I can abstract it using a graph, and then I can represent the actual technology between these lengths using numbers. هتقولي numbers دي بقى how do you model these numbers? These can be modeled in different ways. For example, مثلا this number or this score is proportional to the theoretical bandwidth of this link. The theoretical bandwidth طبعا this is standard. يعني if we have Ethernet, if we know that we have 10 gigabit per second Ethernet, then this number corresponds to the 10 gigabit per second. If we know that this is Wi-Fi, we know that Wi-Fi مثلا 11 megabits per second. So we put this number that corresponds to 11 megabits per second. We can normalize طبعا these numbers and we can put it like this. Okay? So we can do this modeling easily. Okay? So the question now is, if I want to, from node U, if I want to reach to node مثلا Z, let's say, okay, how do I plan the entire path? Well, visually, we can tell what is the path that I should take from U to Z.
1, 1, 2.
So I need to go U, X, Y, Z, صح? Why? Because this will give me. Why did you select this path? Shortest path, or the minimum cost path. If we assume that this is cost, so this is the minimum cost path, okay? Or shortest path, we use it a lot if these numbers are a ones, 1, 1, 1, 1. Rep actually uses by default 1 for all the lengths. Just one. Okay? Regardless of the technology. Which means that I need to go minimum number of hubs. Regardless of the theoretical bandwidth, regardless of the technology. So this is a very abstract يعني, but it's used. It's used, and we'll know some reasons why we actually worry about the theoretical, why we need to abstract the technology in few minutes. Okay? طيب, visually we can do it, but we need to do that systematically. We need to have an algorithm Okay? We need to have an algorithm that gives us this minimum cost path, and we trust that this is the minimum cost path globally. If I want to reach from U to Z, then this is the path. Okay? So remember, I always need to in the routing table, what I need to do فعليا إن أنا from U to Z, I need to go here, and then here, and then here. If I need to go to X, I need to go here. If I need to go to Y, I need to go this and this. Okay? طيب, what if I need to go to V? I will go this way. And so on. Okay? Which means what? I'm constructing now, we call it a shortest path tree. Okay? A shortest path tree contains subset of edges on the graph that allows me to go from one node to all the other nodes. Okay? Because that's what I need to store in the routing table of U. U needs to know what? If I need to go to X, I need to go to this output port. If I need to go to V, I need to go to this output port. If I need to go to Z, I need to also go through this output port. If I need to go to Y, I also need to go to this output port, and so on. Eventually, this is what I need to store in the routing table. Okay? In the routing table, we store all the packet forwarding rules that I need to use. Type. So this graph modeling will allow us to have a set of nodes representing the routers and set of edges that represents the technology and the theoretical bandwidth, or I could actually use these numbers also as a combination between the theoretical bandwidth and the current load, because I have مثلا let's say highway مثلا طريق الشمال. As we can imagine, طريق الشمال مثلا will have very low cost, صح? Because the highway is very wide, صح? But if I have it low cost, this means that many traffic will go through the highway. So after some time, the highway will become a traffic jam. And all the incoming packets, if they go through the highway, they will go through the traffic jam. This is not a good planning, صح? So I also need to take into consideration some statistics about the current load on this link. صح? If I need to maintain efficiency. Okay? As you can imagine here, if we send all the packets this way, after some time this will be jammed. Okay? So after some time, I will defeat the purpose of selecting this link for all this traffic. So we can use a combination between the theoretical bandwidth and the load and some reliability. What is the probability that this link مثلا will go down? I can take that into consideration as well. Because if I go through مثلا company XYZ, chances are 50% of the time it's down. So why do I need to send the traffic this way? So it's not usually a good strategy. Okay? So I can represent this number using combination of measurements. Okay? That's not our challenge right now. Our challenge is that once we put this number, we have the graphic, we have the graph modeling. And now we need to construct the shortest path tree. This is our job now. We need to construct the shortest path tree from one node to all the other nodes in order to be able to construct the routing table. So this is what we talked about. So the cost of a link between X and X dash, between any two links, is actually معروف طبعا. يعني مثلا between W and Z, it's 5. ماشي? The cost between U and Z is the cost of all the links that will lead to Z. Okay? And then the routing becomes to find the minimum total cost that will allow the packets to go from U to Z. ماشي كده؟ So this is easy. So this is the job of it. So before doing that, we need to talk about two classes of routing algorithms. طبعا this is easy. We have static and dynamic. What is the difference? We talked about this in network 1. We talked about this in network 2. ماشي? Static and dynamic. Static routing talks about the fact that the routing table will be inserted in the router manually, which means that there is a network analyst that go to each router, okay, and sort of enters the routing table items. So, for example, if I have a network like this, and we know that we have physical links that look like this, so the network analyst will have to go to this router, insert command, put here in the routing table, all the packets that come from all these sources will have to go this way. Or going to this مثلا source will have to go this way. ماشي? All the packets that needs to go to this destination will have to go this way. So that's it. So I constructed the shortest path tree on this route. And now I need to go to this route. Goes one by one. Okay? And if there is any changes in the network, for example, this link goes down. I need to go manually and introduce some changes in the routing table to reflect this change. So this is static routing. So as you can imagine, static routing is only feasible if you have small topology. صح? Small topology. So if you have a small topology, that's possible. If you have a large topology, it becomes really problematic to use static routing. So we have to resort to dynamic or automatic routing, which means that these routers somehow need to plan this routing path end-to-end automatically. Okay? So dynamic routing is somewhat tricky and challenging. So how do we do this? So that's what we need to talk about. So dynamic routing has to be done in a decentralized way, and it can be performed using either link state or distant vector. Link state is similar to Google Maps. Which means that each router needs to maintain a global view. Which means that all these routers, they will have to exchange information about all the directly connected links, so that after some time, all these routers will have a state about all the links in the network. Okay? So that's what happens in Google Maps. Okay? هتقولي طبعا that's a centralized approach. So that kind of defeats the decentralized architecture. So that's why they have to do this within a domain. They usually do this per service provider. So each service provider will have a large network. So they do link state routing inside that domain of that particular ISP. They don't do it for the full internet. They do it within boundaries. So we can maintain a global view, but it's not a global for the entire internet. It's usually bounded by a specific domain. Imagine? But regardless, link state talks about maintaining a global view. Amen? So if you can ask the same person, I exited the gate from QU, I tell that person, how do I go to دخان? يقول لي خلاص, go left, you will go to مثلا UDST, and then from UDST you will meet another intersection. So go right, go left, go right, go left, go right, go right, until you reach دخان. He can give me the entire path. Because this guy maintains a global view. But for this guy to maintain a global view, we have to exchange tons and millions of these messages so that all the routers, they know about all the links in the network. This is a huge effort. Okay? طيب. Distance vector بقى. For distant vector algorithms, we don't have to maintain a global view. Okay? Each router will, by default, each router knows about the directly connected links. So if I have a router like this router connects with many LANs and WAN links. Okay? By default, this router physically knows about everything related to these links. That's the minimum, okay? Some of these will be connected with other routers, صح? And these other routers can be connected to other things. Okay? This router بقى doesn't know about these links خالص. Doesn't know about these links. So here the router has a partial view. So it has a full state of all the directly connected links and abstract view about the remaining part of the network. Abstract in what sense? So if I ask this guy, I exited the gate, I ask this guy, how do I go to Dukhan? You will say, go left, okay? So, and then you say, go left, and then when you find an intersection, the distance to Dukhan will be 10 kilometers. Type, what do I do after this? I don't know. I don't know. I don't have a global view. I have only abstract view. All I know is that the distance between the next router and Dukhan is 10 kilometers. But where should you go after this? I don't know. ماشي? When I go to the next intersection, the guy will say, oh, okay, so go right. Okay? You will reach to مثلا Daphna. Okay? And from Daphna, you will have 8 kilometers to reach Dukhan. How do I go after this? I don't know. فهمنا الفرق؟ بس link state لا, he will be able to tell you everything. He will be able to tell you everything. So how do we بقى construct the messages and the routing table for each of these two classes? If we have link state or if we have distant vector. So for link state, I need to maintain a state of all the links in the network. And all these links are maintained in every router in the network, which means that all of us will have one link state database that should be identical. It should be identical. ماشي كده؟ For distant vector, لا, I don't actually construct a link state خالص. I don't have any link state. ماشي? So that's why for each of these two classes of routing algorithms, we use different technique, different algorithm. We'll talk about this. ماشي؟ But let's have 10 minute يعني refreshing كده عشان الناس تنام. فخلينا نستريتش كده 5 minutes ولا حاجة. So again, يعني the main difference في حالة for the case of again link state, the router is connected with directly connected links, and these are, of course, we maintain the state for it, but also all the links very far, I still have to maintain the link state for all these links, okay? But in order to know the link states for the very far links, as you can imagine, I need to get information to go back to this router. That's why I need to exchange link states in the entire network. So I have, especially at the beginning, I have a flooding of messages, okay, that happens in the beginning that floods the entire network with link state messages. So the overhead at the beginning is huge, okay? But the only good thing here is that once I do this flooding for all the link states, I do it once and for all, and I guarantee that once I have this global view, I can construct path from any node to any node. خلاص, I don't need anything. For the distant vector, it's different. I don't have states of all these links, but I sort of have abstract distances between this router and any far router, but I don't know I don't have any visibility for this, which means that the distance that's reported from this router to me, should I trust it? Most probably I cannot trust it 100% because I don't have a global view, okay? That forces the routers for distance vector to keep exchanging distance messages all the time. All the time. Why? Because we don't have any global view. دي نقطة مهمة جدا. Okay? طيب, if we were to represent the the updates, okay, these are the updates. The updates for the routing information, the routing information update, okay, between these routers versus time, okay? So for link state, you can imagine that at the beginning, you will have to flood the entire network with huge amount of messages, okay? And then it goes way, way down, and then it becomes very few. So I need to perform reflooding of some messages only if a router loses a connection. يعني one link, خلاص, I lost it. Then this router will have to reflood the state of all the directly connected to all the routers. Okay? So I always need to do synchronization between the routers. So that accounts for this few updates that I need to do from time to time. But at the beginning, flooding, huge amount of flooding that has to happen. For distant vector node, it's something like this. It's periodic, and it has to be continuous. Why? Because I can never trust the distances that come from these routers that this will be really the minimum distance. I don't know, because I don't have a global view. So I require all the routers to keep exchanging these messages periodically. واضح? This is a very, very essential difference. So updates for distant vector are periodic and continuous. For link state, it happens through flooding, which increases at the beginning, and in a later stage, it's very minimal. Okay? Another big difference is that for link state, how do we construct the routing table? هتقولي ما انا عندي اللينك ستيت. Yes, but يعني link state is not the routing table. خد بالك. The link state we have to have two phases. في حاجة اسمها link state database. This link state database has a global view of all the states of all the links in the network. But this is different from routing. Okay? Then in the routing table, I need to construct routing table. Here بقى we need to use a technique. We need to use an algorithm that takes all these link states and construct a shortest path tree that will lead to the routing table. اللي احنا اتكلمنا عليها في الجراف اللي فات. في الجراف, so from the graph will give me the full information about all the link state in the network. I have this in the router, okay? So the next phase, I need to construct the shortest path tree, which means that from this router to all the other destinations in the network, what is the shortest path? So from one node to all the destinations. We call this a shortest path tree. And then in the third phase, the shortest path tree, I need to reflect it in the routing table. It becomes very easy. We'll see now. Okay? So now we need to talk about link state. For link state, we need to have some notations which will allow us to design a technique. We call it Dijkstra algorithm. حد سمع عنه أكيد يعني. It's very, very famous. Dijkstra algorithm, it's some kind of a greedy algorithm that constructs systematically the shortest path between one node and all the other nodes in the graph. واضح كده? So Dijkstra algorithm constructs the shortest path tree from one node to all the other destinations. So we have the network topology and the link cost. So we زي ما قلنا احنا we get this from the link state flooding. From the link state flooding, we have the link state database, which corresponds to the graph. تمام? So we accomplish this through a state of broadcast or flooding to the entire network. So all nodes have the same information, supposedly. Supposedly now that once we flood the entire states of all the links, all the routers are synced. They have identical link state database. Okay? So we compute the least cost path from one node to all the other nodes. We call this shortest path tree. ماشي? So after some iterations, the good thing about link state is that this number of iterations is well known برضه. After systematic number of iterations, we know that this is some systematic number of iterations is k, and k is deterministic. Okay? We can reach to the least cost path from this node to all the other nodes, and this will be the state of convergence. Okay? So the routing table will be converging, and it will be fixed for quite some time until there is a drastic change that happens in the network. تمام كده؟ طيب, the notation for this is easy. So we know that we have the cost for any link, cost between node X and node Y. This is the link cost from node X to node Y, which by default is known for the directly connected links, but initially, for the indirectly connected nodes, it's infinity. Okay? Initially. ماشي? So for example, this is X and this is Y and this is Z. I know from X to Y, it's 5. Okay? From Y to Z, it's 10. Okay? What is the cost between X and Z? Initially, I don't know. I need to ask Y, and Y will tell me. Then in the next iteration, I will know it's 15. But initially, we put it as Y, because we might have another path here with 7. So 7 is shorter. So we need to always maintain, in the shortest path tree, we need to maintain the path with the minimum cost. ماشي? So initially, we put the cost for the indirectly connected nodes as infinity. And hopefully with time, with different iterations, this infinity will drop back until it reaches to the minimum cost. There is also the cost for a particular path, which is a current value for a cost of path from source to the final destination. DV is the total cost between all the nodes on a particular path. ماشي؟ سهلة. And there is the predecessor. Predecessor, this is important. Why? Because I'm going forward, so I need to, in order to go to Z, I need to go to Y, and then U, and then kaza, kaza, kaza. I always need to maintain the predecessor. Why? Because once I reach to Z, and once I reach to the final destination, I need to kind of trace back and know where I came from so that I can know the entire path. So we also need to maintain the predecessor. ماشي? In order to know the full path end to end. N dash here is the set of nodes that I included in the shortest path tree. N dash is the set of nodes that I included in the shortest path tree. Once N dash equals to N, then I stop. واضح? Which means that now N dash is N, which means خلاص, all the nodes in the network have been included one way or another in the shortest path tree. خلاص, that's my job, so I'm done. ماشي كده? That's why we say that the number of iterations is actually deterministic, which is also a good feature in this algorithm. We'll see the other algorithm in a few minutes, or maybe next time. So Dijkstra's is really systematic. Let's just skip this. This is the algorithm, but we need to talk about this. So زي ما بيقولوا كده بالمثال يتضح المقال. We can jump to the exercise, and we will be able to construct and understand this very easily. So at the beginning, as we said, node U knows the cost for the directly connected links by default at the beginning. Okay? هتقول لي ما احنا اتكلمنا على global view. Global view exists in the link state database, which I can consult at any point. ماشي؟ But initially I have to do this in number of iterations. Okay? So if I ask the link state database what is the cost between this link and this link, it will give me. It's not hidden, it will give me. Okay? But initially I have the cost for the directly connected links. ماشي؟ And I can assume that the cost between U and Y is this is not directly connected one. So I put it as infinity. The cost between U and Z is infinity. Okay? So this is the total distances. Okay? And the predecessor for all of them currently is U. So if you go to here, what is the predecessor? U. If you go to X, what is the predecessor? U. صح? If you go to here, what is the predecessor? U. So you always need to trace back which node got you to the minimum cost path. Okay, so this way you can trace back and know the entire path. ماشي كده؟ So we can construct this row. حد مش عارف ليه how we constructed this row? This is very easy. From node U, which is the predecessor for all these entries, we can know the distance. The directly connected one is 3, 5, 7. 3, 5, 7, easy. And the indirectly connected one is by default infinity. ماشي كده؟ طيب خلاص, the next step is easy. From then we can systematically do the following. We select the path, we select the distance with the minimum cost. And this one we include in n dash. Okay? And from then on, we can assume that we know the directly connected links from U or W. Okay? So when we go to W now we can consult the link state database and ask for this cost and this cost and this cost. واضح؟ ماشي كده؟ So this link is included in the shortest path tree. Okay? Which means that U and W are now part of n dash. Okay? So Dijkstra's algorithm is very simple, but it needs some practice. If you do 1 or 2 examples, it's very systematic and very simple. So if you select this minimum cost, include it in n dash, and you keep doing this recursively, you will construct the shortest path tree very systematically and very simple. So we need to add this we need to add node W now to n dash, and from then on we can assume that we know U and W. ماشي كده؟ So this is iteration number 2. So we have U and we have W. This is iteration number 2. ماشي? So the cost between now U and X is either UWX, which is 3 plus 4, or 5. صح كده؟ Which is, we have to go 5 على طول. Okay? Because there is a directly connect. So we know now the cost for this link, for this link, for this link, for this link, for this link. Okay? So the cost to X is 6. Sorry? The cost? For X is 6. This is V. Sorry. This is V. For X is 5. Sorry. For X is 5. For V is here. ماشي? So it's either 3 plus 3. So 3 plus 3, which is 6, or UV directly, which is A. So if I select 6, what is the predecessor? W. برافو عليك. If I select this 7, what is the predecessor? It's U. ماشي كده؟ So this is 6, this is 5. For Y, now we can go through this Y and then 8, which is 11. Or we can go this and this, which is 12. صح? Or we can go this and this, which is currently 13. So it's 11. ماشي? When we do it this way, then now the minimum cost. One thing you should notice in order to make sure that what you are doing systematically is right. Once you select the minimum, خلاص, there's nothing here you need to worry about. خلاص, you don't have to calculate anything from now on for this column. Which means that for each iteration you remove one column, which means that the number of iterations هنا is the number of nodes minus 1. The number of iterations, not the number of calculations, خد بالك, the number of iterations. The number of iterations, the number of steps. Because the complexity is something else. We'll have to talk about the complexity in a minute. ماشي كده? So from this row we select the minimum. So the minimum is 5, which means that now we include x. So here x will have to be included. ماشي? So which means that this column and this column and this column are done. خلاص. ماشي? And now from then on we have to worry about the other ones. So again we do the same thing. So now we have to go through W or X to reach to all the other ones. To go to W and then V, again it's 6. To go to X, and then it's 5. To go from V to Y, again now it's A, for Y it's 11, and so on. So now after reaching to, after we add X to N dash, now there is a node that has become reachable which used to be unreachable before, which is node Z. Node Z is now reachable through X. Okay? And now the cost is a 5 plus 9 is 14. ماشي? So all the infinities are gone, and now we have cost which may or may not be the least cost at this point. When do these become the least cost? When all the nodes are included in N dash. Then we stop. بالضبط, خلاص. If the N dash becomes N, we stop. Once we stop, we know that this is the shortest path tree. Again, iteratively, each step we include one node in the shortest path tree. Okay? So we keep doing this. Now we connect to Y, and next we connect to Z. So this is the shortest path tree. As you can imagine, the shortest path tree includes subset of the edges in the graph. Okay? So from this shortest path tree, we can construct the routing table very easily. Okay? So for example, for routing, this port, let's say this port is 0, this port is 1, this port is 2. ماشي? So what is the routing table now? The routing table for node U, okay, depends on the destination. So if I need to go to X, I need to go to port 0. ماشي? If I need to go to any other node, whether W, V, Y, Z, I need to go to port 1. صح؟ Port 2 is not include خالص, ما فيش ما استخدموش. ايه سوري؟ ما هو اهو. If I need to reach to W, I go to port 1, صح؟ If I need to go to V, برضو I will go to port 1, صح؟ If I need to go to Y, برضو I need to go to port 1. لا, this table is for constructing the shortest path tree. I'm talking about the routing table now. The routing table. Routing table performs packet forwarding, remember, which means one hop forwarding. So I need to map destinations to port number. That's what I need to include in the routing table. معايا ولا مش معايا؟ Now this is the main difference between routing and packet forwarding. Routing, I need to plan the entire route, صح. بس بالنهاية what I need to do is local packet forwarding. In the routing table, I need to map all the destinations to a specific output port. واضحة النقطة ولا مش واضحة؟ There is a difference between linked state database, shortest path tree, and the routing table. Linked state database, we all know, it maintains separate states for all the links. Okay? Shortest path tree, we need to plan the shortest path between one node and all the other destinations. All the other destinations. Routing table maps destinations to output port, which means one hop packet forwarding. واضح؟
أنا قاعد أسوي الراوتينج تيبل حقيقي.
بالضبط. This is the shortest path tree from you to all the other. Of course, خدي بالك, all the other routers will have to do the same exercise, using Dijkstra separately. صح? They will have to do this. V will have to construct the shortest path tree from V to all the nodes and build its own routing table. Y will do the same, Z will do the same, X will do the same. All of them will do once we know that all of them, they have the same link state database. They have a synchronized link state database, so they can construct a shortest path tree from any node to all the other nodes.
لما جبت الواي بطلع بعد على الواي. كنت قاعدة أطالع.
Yes, حتى Y ليه بقى؟ ليه؟ If I go to Y, where should I go? I should go to W first, صح? And then V, and then Y. Okay? So from the point of view of U, I need to send it this way, صح? Which means port 1. Okay? And W, I know that W, when W constructs the shortest path tree from W, I trust that W will select this to go to Y. Okay? And when V constructs the shortest path tree, I trust that it will select this link to reach to Y.
Based on the table of
لأن احنا كلنا we maintain the same global view. Supposedly we all have the same global view. Okay? We all have the same global view, which means that this shortest path tree is constructed in all the routers. حتى V, when it tries to construct the shortest path tree, it will be the same. It will be the exact same one. From V to Y, it will go this way. From V to W, it will go this way. From V to U, it will go this way, and so on. Okay? It's the same shortest path tree because we all look at the same global view. واضح? But shortest path tree, a shortest path tree includes a subset of all the edges in the graph. It doesn't include all the graph طبعا. ماشي؟ When I construct a routing table, I need to map destination to output port. That's it. To facilitate the local packet forwarding. So that's what I need to do. ماشي كده؟ طيب. So the number of iterations هنا, we can say that the number of iterations هنا equals, or the number of steps equals to the number of nodes. The number of steps. ماشي? But the number of calculations I need to do for each step is always decremented by 1. At the beginning, I have to do n calculations, صح? And then in the iteration after this, or in the step after this, I have to do n minus 1, and then n minus 2, and then n minus, and so on. Okay? So this is the shortest path tree. When I remove all the links that are not included in short path tree, this is what I get. So if I need to go to V, I need to go UV. If I need to go to X, I need to go to VUX, and so on. Where do I know this? From the predecessor. ماشي? Algorithm complexity here, why do we say that the algorithm complexity is quadratic? Remember that in the first step, what do I need? How many calculations I need to do, as I said? N, صح? In the next iteration, in the next one, and so on, all the way to 1, صح? This is a sequential series, صح? what is the summation of this sequential series? It's n divided by 2 times n minus 1. Sequential راجعوا الالجبرا. So this is يعني so for us طبعا to derive the complexity, this is quadratic واضح. So it's O of n a, O of n square. ماشي؟ طبعا there is more efficient way of doing the exact same thing using a complexity which is n times log n. ماشي؟ But we don't have to go through the changes that happened here. ماشي؟ طيب. One thing بس we need to discuss now. There is a problem if we were to use the link costs as the current load, the current load, then there is a risk that Dijkstra or the link state will lead to packet oscillation. How?
Packet what? Sorry.
Packet oscillation. Packet oscillation معناها زي looping يعني. Packets will keep going this way and then this way and then this way. They will oscillate يعني. Based on the scenario that we talked about. يعني احنا initially, if we assume that initially يعني the cost of a link, okay, is 0, and if I add a traffic to this link, depending on the load that this traffic causes, the cost will be updated. Another way, it's a real-time cost update. ماشي? Why do we say this? Because if you study dynamic routing protocols like CREP or OSPF, you always read in the book that they use link cost based على theoretical bandwidth, not based on real-time load, with the only exception of one routing protocol. حد عارفه؟ ايه؟ لا ريب بيستخدم number of hubs. Actually, the cost is 1, regardless. OSPF uses bandwidth, but the theoretical bandwidth. يعني if this is 100 megabit per second link, it will put كده and the cost هنا is 100 مثلا. يعني cost corresponds to the theoretical bandwidth, regardless of what is the current load at this point. But زي ما احنا قلنا, if I put مثلا a link مثلا like fiber optic link, okay, so I put cost 0. طب ما all the traffic will go through this link, and after some time this link will be jammed. Okay? So that's why one routing protocol I was hoping someone would mention, EIGRP, we studied EIGRP in Network 2, if people remember. EIGRP uses a combination of theoretical bandwidth and real-time metric. The real-time metric is actually, it's used to measure the load and the reliability on the link. The load and even then it's optional. First, why do we need to use the real-time metric? As we said, because if we use passive theoretical bandwidth, in real time, all the traffic will go through the highway, it will be jammed, okay? If we use real-time metric only, we will have packet oscillation, okay? So that's why EIGRP uses a combination of both. But the fixed matrix based on the theoretical bandwidth will never cause packet oscillation. It may cause some traffic jam in real time, ماشي, but it will never cause packet oscillation. طيب, so تعال نشوف بقى لو real time, لو احنا استخدمنا real time matrix only, real time cost, how does this packet oscillation happen? Imagine if I have a very small network like this, A, B, C, D. Okay, initially, the cost on all these links is 0. Okay, the cost on all these links is 0. And C, it receives an incoming traffic with a load of E. ماشي? And D receives a traffic with a load of 1. And B receives a traffic with a load of 1. Okay? And let's imagine that because all the links are 0, it starts with 0 cost, Dijkstra will say, okay, so the cost is the same, so I decided to send this E through here, which means that now this link will have a cost of E, صح? And because this link receives the traffic from E and the traffic from 1, the cost here will become a 1 plus E. And this one, we decided to send it from D to A directly, which means that this cost is 1. ماشي كده؟ So now it's good. ماشي? But after some time, we recompute the routing, and we discover now that here, when C here we have the traffic E, and here we have 1. So E here, if we send it through this way, it will become E plus 1 plus E. صح? If we send this E, the cost here becomes E plus 1 plus E, which means 2E plus 1. صح? Banana, if we send it this way, what is the cost? 0 plus 1. طيب, what is the minimum cost? We have to send it here. صح? Okay, so let's switch this to here. Okay? شايفين الissue? حتى B will say, okay, so if I need to send this one, this is 1 plus E, and this is E plus 0 plus 1. Okay? But this is similar cost. So I may actually send it here or send it here. Okay? Are you following now what's happening? So what's happening now is after some time, the cost here will become 0 plus 0. Okay? And I have E. So Dijkstra will say, la, let me switch to here because this cost is less than this. واضح? So after some time, I will switch all the traffic to here. And in the next iteration, I will switch all the traffic to here. So I'll keep doing that. So the conclusion here is that you can never, ever rely on real-time metric only. ماشي? That's the conclusion. You can never rely on real-time metric. Full stop. Okay? You always have to incorporate the theoretical cost. A theoretical cost based only on the technology that's used. So if this is Ethernet, and it's 10 gigabit per second Ethernet, so it has a cost. Wireless, 11 megabits per second, it has a cost. ماشي? This is based on theoretical technology, on the theoretical bandwidth. ماشي? So we always have to incorporate the offline metric. We cannot rely completely on real time. Real time will cause packet oscillation. واضح كده؟ ماشي كده؟ طيب. Very small introduction about distant vector and then we'll stop. So for distant vector, as we said, we don't have a global view. We have only small part of the puzzle, ماشي? Just a local view. So we know the cost for the directly connected links, that's for sure. And then we receive periodically the distance between the next node and the final destinations. And somehow we have to have some level of trust that these distances are good. Can we say it's the minimum? We cannot say it's the minimum because we don't have a global view. ماشي? But Bellman-Ford what it tries to do is that it says that I guarantee to you that you will always improve. You will never go worse. Okay? So you will never regress. You will always go forward. You will always improve what you have. You will always improve the partial view that you have. Okay? But is it the best set of vector of distances? I don't know. ماشي? So we have to periodically receive these packets all the time. ماشي? So the idea is very simple. Ho Bellman-Ford, he tries to maintain a greedy approach. He would say that, okay, so as a node, you have the coast for the directly connected links, so you have the coast from X to all the other neighboring nodes. That you have. ما فيش مشكلة. And then you receive some vector of distances from the neighboring nodes. Okay? So basically, if you need to reach to any indirectly connected node Y from X, it's the coast from X to any neighboring node, which you know that coast, صح? Plus the vector distance between this node and the final destination. Okay? طبعا you have يعني different possibilities بقى. Okay? So you select the minimum one. Does this guarantee that this is the minimum? This guarantee is the minimum if this one is the minimum. If this distance is the minimum. But is this the minimum? We don't know. ماشي? And no router will be able to tell you that this is the minimum distance, so I know for sure. Why? Because this router has partial view. It doesn't have the global view. You can guarantee that this is minimum only if you have global view. The link state database used to give us this global view, but we don't have this now. But using this very simple equation, this Bellman-Ford equation, حتى it's not an algorithm. It's not an algorithm. Bellman-Ford equation بس. The whole thing is equation. Very simple. ماشي? I have neighboring nodes. I have the coast for all the links, for the directly connected nodes, and some vector of distances that I receive periodically from these neighbors. So if I apply this equation, I will always improve. ماشي? Improve معناها at some point, hopefully I will reach to convergence. At convergence, what happens? The cost between node X and all the other node is minimum. But can X actually decide this? No. It will keep doing that all the time. ماشي? It may actually reach to some level of trust if and only if I do this Bellman-Ford equation and I see that there is no improvement. If I do this مثلا for 3 iterations, then okay, so there is a chance I reach to convergence. Can I say for sure? No. I can only say that if I have global view. ماشي؟ طيب very يعني طبعا this is very simple. So from you, if I need to reach to Z, what will happen is that at some point I will receive distance of vector distances from all the neighboring nodes اللي هم X و V و W. These are neighboring nodes. I know the cost for these links. I know that for sure. So I receive a distance from node V, I receive distance from node X, and I receive distance from node W. So all I need to do is just to say, okay, I can apply this from U to V plus VZ, from U to X plus XZ, from U to W plus WZ. I need to apply this. Which one is the minimum? 1 plus 3. خلاص. اللي هي through X. Okay? But will I be able to know that I actually go from U to X and then Y? لا, I don't have this. واضح? I don't have this. From X to Z, I have this lump sum or abstracted in distance that I receive. Is this actually minimum? I don't know. واضحة النقطة دي؟ I stress on it very many times أهو. ماشي؟ That leads us to a very specific characteristic that, on one hand, as we said, we have to exchange these vector of distances periodically. ماشي? On the other hand, how many iterations do I have here? Huh? So in link state, we have deterministic number of iterations. صح? Because after k iterations, and k is actually n minus 1. N minus 1 steps. So we have number of iterations after which I know for a fact that I reached convergence because I have global view. Here, how many iterations do I have? I don't know. I don't know. I cannot tell. That's the case على فكرة for all iterative algorithms. It will always improve, but you will never be able to know deterministically how many iterations you can have before you reach to that. All the optimization problems are like this. All the iterative techniques, nonlinear optimization for all of them, they cannot actually give you a deterministic number of iterations. This is a very inherent characteristics in this iterative algorithm, especially if it's based on decentralized approach, which is Bellman-Ford is based on decentralized approach for sure. واضح? So I cannot have a specific number of iterations. But if I have these vector of distances, I can update the routing table based on this. صح? But is the routing table now converging? I don't know. Maybe after a few minutes, I will receive vector of distances which is better than what I have. So I will have to go to the routing table and re-update it. And I will keep doing this. Hopefully after some time, the routing table will be stable. ماشي؟ طيب خلاص this is يعني normal. Let's go through there is a specific calculation and example similar to the distant vector, but let's go through it next time. Although the Bellman-Ford equation is very simple, as we can see, but to apply it on real example requires also some systematic steps that you need to practice. You need to practice how to do it. ماشي? We'll do this next time, inshallah.